Hello to everyone who's watching. We're the group Browser Arouser and this is our presentation of the simulation analysis for the given structural beam. So these are the contents of our plate number 3. First is the stress analysis, the next is the deformation analysis, the third one is the theoretical solution, and the last is the comparison between stress simulation and the theoretical solution. But before we dive deeper into these contents, first we will show a tutorial on how to make and simulate the given structural beam.
In this tutorial, we will going to learn how to create and simulate a square tube in SolidWorks. First, open up SolidWorks, then select Part. Now, if that didn't pop up, just go to File right here and create a new file by selecting the part as we've said earlier. After reaching the working space, what you want to do is to edit the units you are going to use for the dimensions and measurements. You can either go to the options, go to document properties, and from the same property you will see the units, and from there you can actually modify the units. Or you can just easily go to your bottom right and click this property right here, and it will automatically take you to the document units faster, and there you can change the units. In our case, we're going to use millimeters. Select sketch, then select the plane that you wanted to base off your sketch. In this case, we're going to use the front plane. Now, we're going to create a rectangle by selecting center rectangle in the sketch tab. Then locate the origin and create the rectangle from there. After that, use Smart Dimension to create your desired measurement or dimensions. In this plate, we're going to create a 50 by 50 mm rectangle. After that, go to Features tab and select Extruded Boss or Plane. Then modify the end condition by selecting Midplane and change the dimension to 3650 mm. Now, change your view to front. Then go back and select Sketch and select the object. Under the same tab, find the offset entities and just select all of the sides you wanted to offset. Since we're going to create a hollow or a hole, we're going to select all of the sides of the square. Under the offset entities property, you will see a reverse option. Just click and toggle it, and change the value to 5 mm. Then press OK. In order to create the hole, go back to Features tab, then select Extruded Cut. Go to Isometric View to verify if the direction is correct. You can change the values if needed. In this case, let's leave it as it is. Now we just need to do one more thing before moving on to the simulation. Go to Top View, click this eye right here, and toggle View Origins. After that, zoom in and create a circle based off from that origin. Before exiting, go to Features tab, then under the Curves command, click Split Line. Then it will ask you what face or faces to split. Just click the area outside of the circle, then hit OK. After creating the square tube, we are now ready to simulate the object. In our simulation of the square tube, the both ends of the square tube should be fixed, and the only location where the force or load will be applied is at the center or the middle of the square beam itself. So in order to simulate, go to Evaluate tab, and you will see the two arrows representing the other options for evaluation. Just click those arrows and you will find different types of analysis. Today, we're just going to use simulation. Just select the Simulation Express wizard. After selecting that, a window will pop up to your right side. Just click Next to begin. First thing you will see is that it will ask you to select the fixtures in your system. Now, you can directly edit the simulation properties right here to your left. You can edit the materials, the fixtures, and the load applied. In this video, we're just going to stick in the property manager in our right side. Click Add a fixture, then select the faces you want it to be fixed. In this case, we want both sides or both ends of the square tube to be fixed. Just hover and zoom in to select both of the faces. After selecting all of the faces, just hit OK. Hit next to go to load properties. Now, you can either add a force or add a pressure. For now, we're just going to add a force. Add the force to the area of the circle that we have created earlier, so that the force will be exactly applied to the center of the square tube. Then edit the amount of the force you want to apply. In our case, the force is 35 kilonewtons. After that, just hit next and choose the material of your object. There's a variety of materials to choose from, but we specifically need to choose 7079 aluminum. Just hit apply, then close the window and hit next. Now we can run the simulation. It will automatically generate a mesh and it proceeds to calculations. As you can see in the animation, it shows you how the material or object will react to the forces applied to it. But in order to understand the whole picture, let's go to the results. Now that we've run the simulation, we can see the results, the stress and the displacement. Now, if we view the von Mises stress results, a plot will appear, and it shows the interpretation of different stresses, the maximum and minimum stress. Now, in stress analysis, the square tube is being subjected by a force of 35 kilonewton at the center. The simulation gives us an idea that the material is a case of transverse loading of a beam. It is a case of transverse loading of a beam because the given loads are acting in plane of cross-section of the beam, and because the given loads are acting perpendicular to longitudinal axis of the beam. Now, we see that the stress is high at joints and at midsection of the beam, since it is more likely that is where most of the resistance is located, due to its supports. Also, we see that the midsection of the beam has a lower value of stress compared to the joints. Even at joints and midsection of the beam, the inner and the outermost surface of the beam has high stress. So, for the transverse loading of the beam, we figured out that there are two stresses that are being generated in the beam. The first one being the bending stress. As you can see, the face of the tube that is in contact with the force applied, or the inner surface as we like to call it, experiences or undergoes compressional stress. While the other side, or the other face of the tube behind the face that is in contact with the force, the outer surface, on the contrary, undergo tensile stress. And as we take a look closer, the stress in the horizontal plane, which is located between the faces that we talked about earlier, is neutral. This horizontal plane is also called the bending axis or the neutral axis. It is the reason why the amount of stress in that area is not the same in comparison to the stress at both sides of the tube. Now, the second stress is the shear stress. Looking again at the simulation, we know that the center of the tube is in contact with the same amount of force, meaning the cross-sectional area will undergo shear stress. But since the length is a huge factor in shear stress, due to its long length, most probably that bending stress is much more prevalent. But if the length of the tube is much smaller, then it is more likely it will undergo shear stress. The two supports in the system are also a huge factor in determining the stress results, since they dictate how the transfer of stress across the entire system is going to go, with of course relation to what area the force is being applied.
For the deformation analysis part, I'm going to discuss the deformation of the material, specifically a square tube that is made up of 7079 aluminum alloy when being subjected to a force of 35 kN at the middle. But before we discuss the deformation, let's be familiar first with the mechanical properties of our material, the 7079 aluminum alloy, for us to have an idea of what to expect to the simulation. So, this type of alloy is usually used in aircraft parts and mobile industry equipment. Its applications indicate that this alloy has a high strength, meaning it will take a huge amount of load before it shows any deformation. It's also a heat-treatable alloy, which means it sometimes underwent a heat treatment to alter its mechanical properties, such as strength. Now, we move on to the deformation happened to the material according to our simulation. In the recent discussion of the stress, we have learned that the stress is high at joints and at the midsection of the beam, and the impact of the stress is evident to the deformation of our material. Deformation here is manifested on the bending moment that occurs on the alloy. As we can see in the simulation, the bending moment are found at the middle of the beam and the endpoints of the beam. The middle part experiences deformation the most because it has the highest magnitude since it is located at the farthest distance away from the supports of the beam. The bending moment can also be seen at the endpoints, as we can see to the illustration that if we apply a 35 kN load at the middle, we can see that a positive deflection along upward direction is visible at the ends, while negative deflection along downward direction is visible at the center. In the figure D, we can evaluate and see why the middle and the endpoints experience stress and deform the material the most. There are two kinds of deformation, elastic and plastic deformation. The type of deformation that we have here is plastic deformation. It is because when 7079 aluminum alloy was subjected to a load of 35 kN, the material exhibits a permanent distortion and will not be able to go back to its original form as the force exceeds the yield strength of the material.
We have here a square tube having its type, which is 7070 alloy, size of 50mm by 50mm by 5mm, meaning its overall width is 50mm, its overall height is 50mm, and its flange thickness is 5mm. Let us say we have a 35 kN force acting on a square tube, and the length from reaction A to reaction B is 3.65 meters. For us to be able to identify the stress acting on this object, we must first draw a free body diagram representing the reaction at force A on the left and the reaction at force B on the right, with a length of 3.65 meters and a force of 35 kN downwards. We incorporate reaction at A with the reaction at B to equate with a force of 35 kN. Next, we must present the shear force diagram. Notice here that there is a symmetry between reaction A and reaction B. So we can come up with RA is equals to RB is equals to the force of 35 kN over 2, and the result is 17.5 kN. Then here is our bending moment diagram represented by points A, B, and C. From this bending moment diagram, the maximum bending moment, which is at moment C, which equates to 31.9375 kilonewton meters. And to be able to get the maximum bending stress, the formula is bending moment M multiplied by vertical distance away from the neutral axis Y all over the moment of inertia around the neutral axis I. We can get the moment of inertia around the neutral axis I by multiplying the external side of the square tube section B and the external side of the square tube section H raised to 3 all over 12, minus the respective internal sides of the square tube section B sub I and H sub I raised to 3 all over 12. Note that we can get the respective internal sides of the square tube section by subtracting 2 times the thickness W to both external sides B and H. In this figure, to get the moment of inertia around the neutral axis, we multiply 50 mm by 50 mm raised to 3 all over 12. Then subtract the quantity of 40 mm multiplied by 40 mm raised to 3 all over 12. That yields us the result of 307,500 mm raised to 4. To get the vertical distance away from the neutral axis Y, we have 50 mm over 2 yielding 25 mm. Substitute the values to the formula on getting the maximum bending stress, 31.9375 times 10 raised to 3 Newton meters, multiplied by 25 all over 307,500 mm raised to 4, and that yields us 2,596.54 megapascals. To identify the deformation, the formula X is equals to force F, which is 35 kilonewtons, multiplied by length L, which is 3.65 meters, all over the modulus of elasticity E, which is 7.2 E plus 0.10 Newton meters squared, or 72 billion pascals, multiplied by cross-sectional area of the square tube A, which is BH minus B sub I times H sub I is equals to 9 times 10 raised to negative 4 m squared. If we substitute the values to the formula, we will have the result of 1.9715 times 10 raised to negative 3 meters. And lastly, we need to identify the strain, which is the measure of deformation of an object under the stress, and is defined as the fractional change of the object's length when the object experiences stress. To get strain, deformation X, which is 1.9715 times 10 raised to negative 3 meters, divided by the length of 3.65 meters, that yields us approximately 5.4012 times 10 raised to negative 4.
As for the comparison of theoretical and SolidWorks simulation results, we can observe small discrepancy. In the stress analysis, the software programs 1,364 megapascal as the square tube maximum stress, while the theoretical computation shows 2,596.54 megapascal. We can say that there is roughly 90.36% difference. It is logical to have this discrepancy because the SolidWorks specifies the type of material where the force will be exerted, while in the theoretical computation, the formula is generalized for any type of material where the force will be exerted. The type of alloy increases the resistance of the square tube to stress and deformation from the exerted forces. For the deformation, the theoretical and SolidWorks simulation results both display same changes in the material. The middle part of the tube is the most concentrated portion that receives the maximum stress from the forces, and is also the part that demonstrates the bending point or portion of the tube.
So that's the end of our presentation. Please subscribe to our channel, hit the like button, don't forget to ring the bell, and if there's another tutorial you'd like us to make, let us know in the comments down below. Thank you for watching and see you again in the next video.